Alrighty. Cool. I'll zoom up so this can look a little bigger. Okay. Question 2, first part A. This is an endothermic reaction. If you're able to identify that with some reasoning, you were able to get an achieve point. For the merit, they wanted the full explanation. So they wanted details in the fact that you are going to need this to break intermolecular forces between the molecules in the liquid state to get it to a gas. So they wanted that detail. So make sure you have the forces in there. It's actually a pretty easy merit point, I would say. Second part was the Hess's law that we've talked about. You should have gotten negative 203 kilojoules per mole. Yeah, hopefully you guys manipulated those equations correctly. If not, you need to review the lesson on Hess's law. Questions about that? Or is that pretty straightforward? I would say so. Achieved is just recognizing you need to multiply the values. So even if you just annotate on the side and I see a times 6, that to me shows you understood that you needed to manipulate the equations, and that's enough for an achieve point. So always take a guess for these things. Merit was a valid method with one minor error. Maybe you forgot to flip something. Maybe you forgot to multiply something. Maybe you made a calculator error. That would have gotten you a merit. Excellence was valid method, correct answer, negative sign because it's exothermic, and your units with 3 significant figures. So unfortunately, the difference between a merit and excellence is making a mistake somewhere. They are not very forgiving with that. Whereas if this was an internal and I've seen other work, I could be holistic in my judgment. But an examiner cannot be holistic because they're only seeing this one snapshot. All right. Cool. That page has the next calculation I want to talk about. So let's pull up the document camera. You guys can flip it over. We are talking more about enthalpy and the enthalpy calculations. So this one here is going to be different from last year. I'm just going to make it a little lighter so you guys can see it. Some things to keep in mind with this question is that they're going to be really focused on using the heat capacity of water to determine energy change and things like that, like enthalpy. Heat capacity of water calculation is basically looking at the temperature change of the water to determine how much energy was absorbed or released. This is a 2-step calculation that we are looking at. What's really important with this question is pulling out the right information for the right locations and grabbing the right numbers because they're going to give you lots of different things, and you have to think about which equation things go into. This question comes in 3 different formats. The first format is the one that I'm providing for you guys today. It is they are burning fuel and they are measuring the temperature change of the water. That is the first version. The second version that they can ask you is they can ask you to mix 2 solutions together and measure the temperature change. So that's version number 2. And version number 3 is you have some water and you are dissolving an ionic compound usually into it. And again, measuring the temperature change. Like I said, 3 different versions. I will do a lesson on each one so that way you guys don't get confused and so that way you know how to pull out the information from the question. Do keep in mind that the collated questions on No Brain Too Small and the SciPad pages that I have recommended cover all 3 different calculations. So if you can't do some of them now or you're a little bit confused, don't panic because I will go over it. Are we okay so far? All right, let's get started. So we are looking at the combustion of hexane. Let me get some different color markers so we can see what's going on. All right, so we are looking at the combustion of hexane, and we want to figure out the enthalpy that is going, or sorry, let's read the whole question. The enthalpy of combustion of liquid hexane can be determined by burning a known mass of hexane and measuring the temperature change of a known mass of water. So we have been given 5 grams of hexane that is burned. So this is my mass. I'm going to write N because that's an important kind of thing. I like to go through and annotate everything that I go through, everything that's questioned in the statement, so that way I know how to pull things. When we're talking about the mass, we're talking in this case of what is burning. So that's the hexane. What I have to keep in mind is that in this question, there's going to be two different masses they give me, and I need to make sure I grab the right one. So they say the mass of hexane is burned, and we are measuring the temperature change of water, and the water is 400 grams. Again, I have another mass-based question, but in this case, this is the water. So I need to be mindful of which mass I need to grab for which situation when I do my calculations. The next thing I see here is a temperature change. It says that the temperature change is from 20.5 degrees Celsius to 36.7 degrees Celsius. So that is a change in temperature. I'm going to annotate that by the delta symbol for change and T for temperature. They want us to calculate the enthalpy of the combustion of hexane. And they've given me some different bits of information. They've given me information about the heat capacity of water. This here is a constant. So it's always going to be that 4.18. And they've given me the molecular mass of the ethane, which I will use later. I'm just going to underline that too. I personally love to color code because it helps me kind of keep everybody straight and in order. I know what's going on. There will be two equations you will need to use for this question. Keep in mind that both of these equations will be given to you in your resource booklet, so you do not need to memorize them. The first equation is looking at the energy that is involved in the temperature change of the water. That is known as my Q value. So Q is going to equal the mass of the water. I'm going to try to keep to my color code, M, times the heat capacity of water, which is my C, times organic people, the temperature change of that water. So that's my first equation. Q equals M times C times the change in temperature. Are we okay with that so far? All right. So I have my mass, that's 400 grams. I have the C value, my constant for the heat capacity of water. It's 4.18. And the temperature change I also do have, it is 36.7 minus the 20.5. So that'd be 16.2 degrees is my change there. So let's plug in those numbers. So Q is equal to my M. My M is 400 grams. So this is the first example of you needing to grab the right gram number. We are, in this case, grabbing the change in temperature of the water. So I want to grab the 400 and not the hexane, which is 5.22. So make sure you're grabbing the water mass. I then multiply it by the heat capacity of water. This is going to be a constant. Again, they will give this on your resource sheet or in the question. You're going to be using this for all your questions. Even if they give you a solution, they're going to say assume heat capacity of water. So you don't have to worry about using a new number. It's going to be 4.18. And the units for that is joules per gram per degrees Celsius. I like to include all my units so that way I can cancel them out and make sure I've done my calculations correctly. And then we multiply by the temperature, which is 16.2 degrees Celsius. Are we okay with that so far? I'm just going to bring up my calculator so we can do that math. I just brought up the camera. I want the calculator. There we go. Okay. So we're doing 400 times 4.18 times 16.2, and I get Q is equal to 27,086.4 joules. At this point, I am not rounding because I am not done with my calculation. but that's how much energy that needed to be absorbed, from the water needed to absorb to do that temperature change. And if I want to double check my units, I see that grams and grams cancels out. Celsius and Celsius cancels out. I'm left with joules, which is what I want because I'm trying to figure out enthalpy. Are we okay so far? Keep going? No, Brooklyn's like not ready. Ready? Okay. The next calculation is our enthalpy calculation. So what we do is we have delta H is equal to the negative Q value that I just found divided by the amount in moles of the reaction. So this N here is going to be regarding the reaction, which in this example is the burning of hexane. So I want to know the amount of hexane that I burnt. Now, part of the problem is that the hexane that was given to me is in mass, and I got that mass to be, 5.22 grams was burnt. So now I'm using the other mass that I saw on the question. Pull the correct masses. In this case, I want the mass of hexane. Now, unfortunately, this mass is not moles, so I need to do my conversion. We know N equals M divided by big M. That's how I convert from mass to moles. You guys did this in titration. So I would do N is equal to 5.22 grams divided by the molecular mass of the hexane, which they've given me over here. That was 86. Again, I like to write down my units to make sure that I'm canceling guys out correctly. Grams cancel with grams. I have per mole, so I will get an answer in moles, which is what I want. So 5.22 divided by 86, I get a long number. Keep them long. I'm just going to do ... to save myself the writing time. But that's what I'm looking at. Keep going. Okay. So delta H is going to be equal to my negative Q value. So I found that in my last question. It would be negative 27,086.4 joules. And I'm dividing it by the N value that I got. So that would be 0.06069 ... moles. I'm feeling lazy. All right, so 27,086. All right, cool. I get my delta H equals 446,309 with lots of numbers after it, and that's joules per mole. What I want to do is I want to convert that into three significant figures, and in fact, I can also convert this into kilojoules if I want. You are not required to. I like to convert things into kilojoules because I think it looks nicer. If I was to convert it from joules to kilojoules, I'd be dividing by 1,000. So I'm just going to divide by 1,000. I would get my delta H equals, should have my negative sign, negative 446 kilojoules per mole as my final answer. So joules to kilojoules is divided by 1,000. And that's that one. Questions, concerns, comments at this point? The calculation isn't too bad. I think it's probably easier than last year's, and I think it's easier than Hess's law in some ways. Did I do something funny? Why? It's less negative. Why is that number different from my number? Hold on, let me just check the NZQA answer, because I might have forgotten a zero somewhere. Let's see. I might have done something in my... Oh, I got the right answer. Okay. Just wondering why I did that. Okay, that's fine. All right, you ready to move on? All right, last question here is now looking at the theoretical part of this section, which is explain why our experimental value is less negative than the theoretical value. So the theoretical value is that we should have had 4,163 kilojoules per mole from this reaction, and we have actually only calculated negative 446. So it's quite a big difference, and the question is why? The reason why is because that heat has not actually been transferred to the water as expected. It's been transferred to the surroundings itself. So since it's been transferred to the surroundings, it's not actually heating up the water. So the heat's getting lost. So basically what we're thinking about is that I have lost the heat energy to the surroundings. So I need to insulate it better. So system needs to be insulated better. If I insulated my system better, then more of that heat would be transferred to the water and I would get a more accurate measurement. Questions, concerns, or comments? And then once you guys have that copied down, I'll go over to the marking schedule so you can see how the points broke down for this. Ready for me to move it? All right. Let me just show you the marking schedule. So, same calculations that I did earlier. They converted from joules to kilojoules a little bit earlier than I did. Doesn't really make a difference. And they will still accept the answer if you had it in joules per mole. It's an unnecessary step, but if you want, it's there. Lots of achieved points for this question. There were 3 possible ways, but they didn't let you take all 3 points. They gave you 2 out of 3 as the max. first correct calculation was calculating the Q value correctly. Second was the correct calculation for the mole conversion. So that was, let me just get this step over here. They gave you an achieve point for that. The last one was correct calculation for the delta H. So not necessarily the right answer, but you've carried the wrong answer through and you've done this step correctly. So that's what that one was. Next one here for the merit then was correct process to determine the enthalpy of combustion, but there is one error. So again, this is what I keep saying. Show all your working. Don't just write the final answer down, because then an examiner can backtrack and see where the error was. If it was a minor error, they can give you a merit point. If it wasn't a minor error, but you've done steps correctly, then they can give you some achieve points. And then excellence was correct answer with unit, 3 significant figures, as you normally see with a lot of our calculations for chemistry. So nice, hopefully easy excellence point for you guys. This one here is talking about that theory question. So it's loss to the surroundings, or, and I totally forgot about the other one, incomplete combustion could have occurred. So maybe the fuel did not burn as efficiently as it should have. There's the apparatus absorbing the heat. There is standard conditions may not be normal, that sort of thing. So when we say standard conditions, we're talking about 1 atmosphere pressure, 25 degrees Celsius, basically like normal kind of lab setting. One reason the achieved for the merit explains the difference. So what I did with my answer, you'll see, is that I'm making sure I tie in. Go back to my camera, open up camera. What you'll see with mine is that I did a therefore. So I'm explaining the reasoning behind it. So not only is it losing the heat to the surroundings, but because it's lost the heat to the surroundings, the heat is not getting transferred to the water. So making sure we have a reasoning for it, not just heat lost to surroundings. All right. Questions, concerns, comments? Hopefully it's a pretty straightforward question. We will do more like these, but like I said, we're going to do them in the different styles. So mixing the solutions together or dissolving something. But I'll hold off and do that in the next couple lessons. All right. Cool. So that's us for today. If you're not feeling confident, do the SciPad pages to help scaffold. Or you can do the collated no brain too small questions if you feel more confident. Keep in mind that they do have the other types of calculations in there, so don't get overwhelmed if you see something and it doesn't look familiar. Just skip it for now, and you can go back to it later. Other options, you work on some organic chemistry in the remaining 15 minutes. Sound good? Alrighty.